So today I will be telling you about what I think will come next after the current AI hype, what will be the next hype. So, and that would be moving from the massive cloud to tiny devices. It is partially already happening, but we are really just starting out. So yeah, a little bit about me. I'm currently sitting here in Kalmar. If you don't know where it is, here's the map. And we have Linnéuniversitetet, so Linnaeus University, that's both in Kalmar and Växjö. And I am data scientist, developer, teacher, you name it, with Mikkel. We worked together before at IoT Lab when I was doing my PhD in bioinformatics. And since then, because of family, I moved here and also gradually moved from bioinformatics to this field of IoT, which I came in touch also at IBM, where we also worked with Mikkel. So it's really fun to have this, to be back a little bit with you. And here at LNU, I'm financed by these wonderful organizations, which I have to name, Region and Tillväxtverket. That's the collaboration with EU, where this IoT Lab is a project where we help companies come sort of get started with anything hardware related, or it can be broad IoT, applied IoT. And we work with anything from startups to large organizations. And it can be anything from lecture, workshops, building a hardware prototype for them, some research and testing. And this is how the lab looks like. It's pretty messy. We have 3D printers with a bit like a makerspace, soldering station, and tons of different hardware that both students and companies can borrow. So if you're ever in Kalmar, come and visit. And there is a lot of these maker spaces. I know that there is one in Stockholm as well, with collaboration with KTH. And then there are also, so if you want to get started in the field, there's a really good tip to join Makerspace. There are föreningar, unions as well, that share this like equipment, so you don't have to buy everything on your own. So story until now has been that you probably also in your daily life use AI in the cloud, and in the IoT field, that's also how it's been for many years now. You have a bunch of sensors. It can be smart city, it can be home automation, it can be industrial automation. So we do have sensors everywhere. IoT is pretty mature field, and we're gathering tons of data, but usually we send it through a pipeline, right, to a cloud server. Sometimes there is like a device, a landing device in between. Can be mobile phone, can be a stationary server at the factory or something like that, but mainly the processing is happening in the cloud somewhere. And there are a lot of issues with that. One of them is data privacy. That's always the question like that comes up. Is my data safe when it's being sent by the sensor? How easy it is to hack this pipeline? And then it's also latency. So there is, even with pretty good connection and throughput, even if you have like automation project on Wi-Fi, there will still be latency, and often you have to, you want to have at least inference instantly. You want to know if there is an alert of a security camera on device. You don't want to wait until the response comes back from the server. So that's where the edge-based approach is gaining popularity. And that's basically, because of real-time insights, reduced latency is the most, is the biggest sort of motivation for that. So that makes the next wave of the edge AI when inference will happen on device. And that's a pretty big field. If you just Google Edge AI, it can be anything from like Raspberry Pis to pretty powerful machines that are still called edge. It's basically, in this case, it means that it is happening where the data is collected. So it doesn't have to be a super constrained device. Usually what's happening now is that, we just pretty much make tiny but pretty powerful computers that are deployed at the same place where the sensors are. Be it whatever factory or city. But there is a challenge with that, which is that they need power. They need power supply. They need support, and they need connection. So that's where the movement goes towards more tinier devices that can run on battery, that don't use that much power, and that can run sort of independently. You kind of forget about them for prolonged periods of time. But that's a challenge with that they are very constrained in resources, of course. So this type of devices then can look like this. This is, I think, something from Google. So that is like one of those, if you've seen Raspberry Pi, that's looks a bit similar. So it's basically a full-on computer which runs Linux. So that is the easy part. And then there are microcontrollers. They're pretty small. So this is all like is a development board where the actual CPU is right here. Same here. This is like a pretty powerful development board. That's what usually I have a bunch of them. So like when the CPU is like this small, and then you have development board is like this, is like a disco board. So you can this is so you can develop for it and easily connect sensors and debugging output, because otherwise you can't really talk to it that easily. But once the device is ready, even with connectivity and everything, it can be as small as this. So this is it's still a prototyping grade board. Inside it looks like this. We will look at it later, which has a CPU, RAM, storage, and in this case Wi-Fi and NB-IoT, so like mobile connection. So it has a tiny SIM card that is using to send the data. And this is how small it is, and it can, depending on what you do with it, it can run from several days to several months or even a year, just battery powered. Battery is also included. Half of this is battery. I don't know if you see this. That's the size constraint usually, is that how much power you need, because that's where we still struggle, is to provide power to these devices. That could be a whole different presentation on energy harvesting and solar power for IoT. But that's still in sort of research grade. So we go forward. What is this AGI or TinyML that you maybe have heard this expression? Is basically the intersection of machine learning and these embedded systems, these devices are also called. It's basically, definition is that is running machine learning models on this low power resource constrained devices that I showed you. And the Y again is low latency. And another thing is also high privacy. So basically the motivation is, we don't want data to leave the device. And that's especially important in security applications and in healthcare. There are very strict regulations on gathering healthcare data, and that includes sensor data. So even if you have like a smartwatch or a smart ring, if you use it in research or in companies, it is regulated, and people are concerned when the data is going somewhere else. So to that degree that is possible, we want to process it on the device and only send maybe the ready-made inference. And it's also, of course, helps us to limit amount of data that is getting sent back and forth. But what does it mean in resource-constrained devices? Yeah, so think kilobytes of RAM, not gigabytes. So that is the main challenge for machine learning models. We don't have that much memory, and also for power, we basically have milliwatts of power, and we have to, whenever we run inference, we have to see how much power is getting consumed, so we don't run out. So then the challenge for us as cloud data scientists, as I label this, is like the generated by Gemini. Using cloud AI, this is us here to the left. We have Python, we have deep learning, we have a lot of ready SDKs, huge resources often. They are pretty accessible, and we're kind of used to be able to access all of it, and pretty much computing power is relatively cheap also. So even though sometimes we try to optimize something, in practice you have a lot of standard solutions that you just run in the cloud. For embedded data scientists, the hardware is constrained, and you often don't have access to high-level languages. Now, C++ is also sometimes considered high-level, but it's basically what you have: C, C++. And even though a lot of this, the field is developing, so each type of like hardware has now their own ecosystem, and it is quite great support with libraries. So like this one from Nordic Semiconductor that we will look at a little bit more today, is based on Zephyr. So that's also one of the things that it's basically like a set of it's a framework for embedded, which has a lot of things that are already there. So even if you are not like a C++ guru, it is possible to get started pretty fast. But then you have to have understanding of low-level memory. So like really, like if you have taken like Civilingenjör in Sweden, or data technique, this was like first courses, like how is actual computer memory organized, what are the registers, what is a modbus, how do I communicate with the device, like through serial. So the thing is that, like in my case, I have forgotten long long ago, and now they kind of coming back, and you have to read and to understand this. Otherwise, even with all the support, it is difficult to debug, most of all if you have an issue. And then here is completely like the GPT and all of this large language models completely worthless. I wouldn't say completely worthless. For basic stuff, they're still good. But if in web and even in data analysis today, you GPT-5 and 5 minutes you have your data analysis, here is just going to hallucinate a bunch of stuff that is not even related, especially if it's a more narrow platform. So how much resources are we talking about? So this is one of the platforms or one of the boards, development boards, that is really exciting. It costs about 500 kroners, and it's from Arduino. So that's a sort of hobby grade. If you have ever done or maybe heard of embedded projects, Arduino is pretty big in the hobby space, but it's relatively powerful, so you can actually develop high performance applications. And a lot of startups actually start with Arduino based projects. I often like to open up like some devices, and you can often find this ESP32 and Arduino boards in things that are deployed sort of in production. Can be anything from like electricity meters to home automation. The reason, because it's cheap, and because there is also a lot of things available for quickly developing firmware, so software for this board. And this little thing here from Arduino actually has pretty powerful sensors. For instance, one of them is BME 688, which is a gas sensor with integrated AI from Bosch, which means that you can train it to identify certain smells or react to certain conditions in the air. So like one of their presentations is when they distinguish between coffee beans from different countries. So like that's how sensitive it is. And in this case, you have ARM Cortex-M4. This is still pretty powerful for embedded, but it's 64 megahertz. If you can see, you can look now on your computer how many gigahertz you have, right? So, and then you have 64 kilobyte RAM. So that's a bit of a big challenge of making models run on such constraints. And that's two strategies. There is often that you have to optimize your code, and you have to really pick when you want to do inference. So like this 688, it doesn't continuously run inference. You have maybe like you trigger it, you have one chance, and then of course the the accuracy and sort of amount of things you can do like is limited. If it's classification, we maybe cannot distinguish 25 different classes. We want to know if it's a coffee or if it's cleaning supplies. This sort of kind of has to be realistic. So this type of boards like Arduino or Raspberry Pico that I'm also going to show today is a great start to sort of try yourself in embedded. And I really recommend it as a data scientist. There is, it maybe looks intimidating if you haven't tried it before, but the threshold is even lower if you start with Pico. So this green thing here is a Raspberry Pi Pico. So maybe you heard about Raspberry Pi, the tiny computer, right? This is even smaller. So this is their microcontroller offering. It still has a pretty powerful processor, which will let you run even simpler machine learning models, and is compatible with the Edge Impulse framework that I'm going to talk to today. But the thing is, you can program it with Python. So this really, a lot of things like communication with different GPIO pins and all the other peripherals is abstracted, and all you have to do is import a library. So this really will let you kind of see what you can do with it. And then, of course, you will need like some other things like a breadboard and some sensors. So like on the board, there is no sensors. It's just like an LED and basic computing. We have a course at the Linnéu, goes every summer, which is exactly the purpose is for this, like getting programmers from other fields to get into embedded. And there we basically build a simple project over like 7 weeks with Python, and people build all sorts of different things. Like I think my favorite from this year has been a popcorn machine. So like, or popcorn dispenser, I think it was. So like automated with an RFID tag, and this is like my level of project. This is now detecting you and is playing Blinky Little Star on this device. So it's like modulating sound to play music and sort of alert them. This project is you can do kind of on your own as well. What you need, everything that you need is available in the starting kit. There is one from ElectroKit, it's a Swedish company, and there's one on Amazon. I think that one costs like 400 kronor. ElectroKit doesn't like when I when I advertise Amazon. But yeah, it looks like this. It comes like a box with everything you need and all the tutorials, and you can build stuff like this to really kind of understand what are all these things. I don't know if you have taken electrical engineering, then you know like why we need resistors and how to connect basically an electrical circuit. But this really helps, I think, to understand how it works on the lower level, even if you develop more advanced models. Otherwise, it will be really really difficult to kind of get to know when there is some issue, right? And I myself was really like intimidated first when I saw people doing this, even though like I had some background in it like a long time ago, but I'm like, I don't know. And the thing is, like, you just have to get started and get a few things broken. So I think the first time I tried to connect a LED, I burned like 6 LEDs because I was connecting it in the wrong way. And a lot of students also burn. Like, it's pretty easy to burn this device. Like, basically, if you give it too much power, it actually starts burning. But it's not dangerous. Like, you don't get like electroshock or something. It just smells like burned electronics, and you have to buy a new one. So that's why it's good to learn to borrow from Makerspace. This is kind of part of it. You will break stuff to learn how to build stuff. Probably the same with software, right? So then once you kind of done your hello world on the breadboard, I would recommend going to Hello World in TinyML. And then, of course, like if it is possible to go straight here, but as I said, like it is really nice to do something hands-on. It can be also as simple as just opening up some IKEA sensors and trying to see like, okay, how does this actually work? Adding them maybe to your home assistant. So it can be even simpler than the breadboard, right? So the next step then, this TinyML is often, we do have still access to all of our regular toolkits, right? Where there is TensorFlow and PyTorch, and then we kind of want to squeeze it in on this tiny device, and then some magic happens in between. And what is this magic then? We basically have to convert the model, if it's written in Python or even if it's C++, whatever, we still have to convert it and optimize to run on this small constrained device. One of the first sort of steps there, can't go back. Is quantization. And if you haven't heard of that before, don't worry. But basically, to simplify, on a computer, like on a regular computer, we work with floats, and they take 32 bits. We don't have that many bits often, and even though like now is many more sort of CPUs that come or MCUs, microcontrollers that come out with support for float, and they're much more powerful than some of those that I showed in the beginning, right? It is still good to optimize. Especially if we want to run some of those like image recognition or voice recognition, some of the heavier models, because the result would be that your model size, so like how much your code kind of will take on this device, will be reduced by a factor of 4, and it's also often faster, so your inference will be faster. That you can also kind of try to, even if you have some dev board that supports float, try to deploy a model with and without quantization and see the difference. And then there's a code generation, of course. If it has been in, if your model is written in Python, it will be converted. It needs to be converted to a C++ at least array for them to be compiled together in a firmware. So basically, when when we deploy code to these devices, it just has to be compiled binary. That's the only thing that this thing understands. And for that, we need C, C++. So it compiles in a certain way. Then you already have kind of a backbone standard firmware for most of the platforms, and then you kind of have to build in your model in there. So you often link, and if you have done C++, you're gonna have to link it as a library. Basically, it's not more complicated than that. And then there are different compilers that do it, and TensorFlow is really has come a long way for this. So if you have worked with TensorFlow, going to embedded would be much easier, because they already have pretty great support for that. So then our workflow for motion recognition is on this Thingy91. So that's the dev board from, don't remember how much it costs. I think also about 400. It is really powerful though, and it has connectivity. And when you buy it, sort of, you just plug it in and it's already sending data to to their cloud. But yeah, this is a step up from a Raspberry, because it's very close to what is actually used in production grade devices. NRF is used in vehicles and in industry, and they are also really big now on wearables and healthcare. That's what we will talk before. I think I'll do like this. I'm not gonna I can show you a bit of the platform at the end if we have time. And now I just basically tell you a little bit how this works, because it will be too much with like switching switching the sharing window. But Edge Impulse is basically a web platform. You can open it maybe on your computer if you want to have a look. It's a web platform and Python SDK for developing machine learning models. And it has amazing support for TensorFlow, PyTorch, pretty much anything you want. And also quite a lot of boards are natively integrated in it. That means that you don't have to like do this and kind of connect a bunch of things, go low level. You basically just click through, and there is like a Node.js nice app from the terminal where you just write like I think it's an Edge Impulse data forwarder, so it connects to this board. What's happening in the background is you're gonna have to flash it with that firmware that they provide. So like that's not it's not magically connecting, but they provide code for that you can just put on the device, and it can directly send data to their platform. So in the case of this motion recognition, you can gather data. So motion recognition in this case, like he's doing like this, it will be able to infer this up and down, snake, or if it's still. So I will show you why this is this is relevant. And then you can also upload training data that you have from other sources. There are a bunch of sources on Kaggle, and they provide also ready-made data sets. You then create so you can collect data, you can extract features from it, so you can do some simple signal processing, like Fourier transform often is needed, for instance, if it's any type of sensor data. And then depending on, you can kind of tune what you want to have higher weights or lower weights. You can also upload your own feature extractor from other sources. Then you can test your model like preliminary and see like if it's clustering, if it will be good results, and finally deploy the model. So it has all these steps for quantization, optimization, and compiling. So in the background there, they have a set of jobs that are running in the background. So every time you kind of submit something, it's doing it asynchronously. Then for the free version, that's like the downside. It will take a bit longer time for you. And if you pay premium, then you get basically more resources. A good thing for that is after you kind of test all of this, it will become much more clear how to do it on your own. So in the end there, will show you can just export the model both in Python and see like how they have written it. And how it works, and then you can do the same tools locally. You can use the same kind of optimization compiler, translating to C++. All of this is available open source, which I think is really cool. That's also, I think, this change kind of happened just in the last 3-5 years, where it's like democratizing embedded development. And making it much faster. So you can, in principle, write soon probably in natural language, right? And then the tools will generate C code that you can deploy on this microcontroller. Now then a little bit about why. And for me, this all started with intelligent wearables. I've been always like curious about smartwatches and how it works. I have also tried Oura Ring. You maybe have heard that there's this exploit. Yeah, you have one. You see, yeah, exactly. So I will show you like a bit of a personal project that got me into this. But this, I think, is the most promising and exciting area of embedded development. And of course, we have like Apple and Apple Watch, and a lot of people are happy with it. Yeah, it's like advanced heart rate monitoring. They promise even early detection of heart disease from their data. But there are a lot of tools that are needed in more narrow fields and that are more personalized. So I think there's a lot of things will happen. There is no image on this slide. Okay, that's fine. So one of the projects that we're working on right now is actually you can say Apple Watch for dogs. So it's a smart collar, and those who have pets, you probably have been using these things. Often for cats, you want like a GPS tracking. But this is like a step up again. So usually those devices just send some data away to a mobile phone. In this case, the ambition is then to detect health issues with the sensor fusion. So this will require kind of much more advanced algorithms on the dog. And one of the things that came out quite recently that we will be able to try is this. I can't even call it a sensor because it's like a lot of things. So this is really tiny. You can't even see it, like this small, and it has an integrated processor. So besides of the host processor on the device, there is a tiny MSU inside this thing, BHI 385. So it's basically a programmable sensor, and it has an accelerometer and the usual data there. But the difference is that you can develop your own models for personalized classification of activities. So this toy project that we'll discuss and kind of look at in Gympulse can go pretty far. So you will be able to have the same kind of grade of like if you're playing golf, if the dog is waving tail or if it's sniffing itself, if it's playing with a toy. So that type of classification, which is live on the device. This Motion AI Studio is not released, so it's basically Bosch, of course, has their own tools for everything. For that gas sensor that's smelling coffee, there is a similar kind of tool to Edge Impulse where you can train and develop and deploy your models. And here they promise a similar thing. So this would be really fun, and just gotten that tiny board home. We'll see how this works. This is also a startup, so we'll see. The the initial project that I want to talk to you about is the open seizure detector. So that's a research project which also uses accelerometer data, but for seizure detection. It's completely open source. There are a bunch of things on the market that are very expensive, especially if they are medical grade certified. So seizure is like, if you're unfamiliar with it, is if you have epilepsy, you can have this like fits or attacks when you lose consciousness, and often have like repetitive, either repetitive motion or just very flexing all the muscles kind of at the same time, and it can affect parts of your body, the whole body, and it is very dangerous. So like, if you have to always have someone beside you, like if you're having this attack and doesn't go away on its own, you have to have someone to give you medication, and eventually even call 112, like if you need emergency care. And one thing that is completely shocked me is that, for instance, in Sweden, you're not prescribed any type of monitoring if you have this disease. So my son has epilepsy, and when we were discharged from the hospital, I asked them, okay, how am I supposed to help him at night if he has a seizure? And their advice was like, yeah, you can sleep next to him and have your hand on him. And I was like, what? So yeah, basically, because there are no devices that detect it with the accuracy that is sort of needed to be classified as a medical device. There are some mats that you can have, like mattresses, which instead have a lot of false positives, so they alarm you about every little movement. So it's not a trivial problem. Luckily, there is in the world another researcher that is working with this, who also has a son with epilepsy. So then there's the growing community basically that is working with providing a much cheaper sort of way to detect these things. And the thing that helped us a lot with this is emergence of open source hardware as well. So if you want to develop things for smartwatches, you don't have to hack Apple Watch, which is pretty difficult, or develop only for it. And for the audience that can buy it, these things cost like 300 kronor Bangle GS, and you can program it yourself with JavaScript, hence the name GS. And there's a bunch of other things that are more open. Initially, open seizure detectors deployed on Garmin watches, which also have a little bit more open SDK. But the issue with this now is, of course, that yeah, the connection here often breaks to the phone. The algorithms are not as accurate, even though they are infinitely better than not having anything. But there are algorithms based on deep learning that actually can classify and identify seizures pretty well. So this is how it basically often looks like. You have accelerometer data is XYZ, basically your position in space, and if there are repetitive motions, even if they're very subtle, you can see it in the raw sensor data. And if you can see it visually, that means that neural network can do that too. So that's basically what the next step is. Unfortunately, I don't have that much time working on this project, but If you are interested, if you're a student or want to do a master thesis or in any other way interested, please do contact me. We have a crowdsourced database, basically with quite a lot of these things for training models, because everyone who is using these things at home, they can opt in to submit their data for research. And then the consortium has sort of access to anonymized sensor data. So that would be really cool to develop a better model that can run on a more constrained device, even when it's offline. So that's basically another project with wearables, which is pretty cool. And this wearable, Emotibit, is also completely open. And it is as powerful, even more powerful than Apple Watch, which is really cool. It has a bunch of sensors that doesn't look as nice as Apple Watch. So here on the video, Patrick, my colleague, has it here on his wrist in a 3D printed case, and inside it looks like this. And it has anything from the PPG, so like the heart, you can monitor heart rate and even stress and sweat. So it has like a sensor measuring on the skin. And a bunch of other things. Basically, this is the electrodermal activity, fancy word, which basically you can derive your micro sweats, so to see how stressed you are. And there, the ambition is to develop a personalized activity tracker. Patrick and the Sports Science Lab there, they work a lot with sports rehab and with elderly. And if you ever tried any of the smartwatches on anyone who's older, has sort of is more overweight maybe, or the opposite is smaller, a woman vs men, you probably have noticed that the algorithms that are actually deployed, even pretty like recent Apple Watches, they are not optimized. They don't learn from you. It's basically, you have this formula, like when you create your profile, you say, yes, I am, in my case, like I'm a woman, I weigh 67 kilos, and then it kind of approximates things. But this will not work if you have any type of motorical condition, or it won't be able to actually derive any useful insights for you. For instance, if you have a blood pressure condition, how much activity is actually going to improve your condition. And for that, we need, like, the data needs to be much more granular. And the models need to self-learn, sort of, again, on ideally on device. So that's also what we are working on. So the key takeaways before we look a little bit around on how Edge Impulse looks like is that the hardware is accessible. From like 400 kroners, you will get pretty far to kind of learn the basics. Then it goes up, like if you want to work with the real things. The tool chain is also finally very mature. So with platforms like Edge Impulse or with any other platform, you also usually have a tool chain that supports you from the data science journey to low level. So you don't have to be intimidated or think that you have to become a C developer. And the biggest asset is still data strategy. So it still starts the same way. We have to collect data, a lot of data, to try to optimize the model first in a sort of theoretical setting before we go to the device. And on this steps, when we try to optimize it for around constraint, we'll probably lose accuracy. We have to have robust validation to try to see if it actually actually works. So everything you know already of how to develop machine learning models, of course, stands. And yeah, to start with it, just get yourself some hardware. You can actually also start just on your phone. It still kind of simulates the edge device, even though it's much more powerful. But on Edge Impulse, you can use your phone as a data collection device, or to run, to kind of test run this whole pipeline. So for instance, if you want to try their voice recognition project, you can teach your phone to certain commands and deploy it on, I think at least on Android, it works pretty well. And yeah, if you want to get in touch with me for any projects that I talked to you today, it's LinkedIn or email that is best. So this was the live classification. So here I have a board connected. This is my my thingy, and it says like, yeah, I have accelerometer, light, environment, or like combination of the sensors, and you can either use it for data acquisition here. In this case, you connect to it with your data forward and then start sampling. But here it should appear then. And then you have this impulse design, and impulse is basically the model. So, but all of the steps, or you can say like a data pipeline. So impulse takes raw data and uses signal processing to extract features, and then you have the learning blocks. And in the learning blocks, this is the basics, right? You have classification, regression, and anomaly detection. These are like the basics of IoT. I know 99% of IoT projects is one of this. So it's pretty much enough. So for this project to classify, to distinguish between the motions, that's the classifier that we use. And it's a very simple spectral features that are here. Here, once you generated the features, that's you probably looks exactly like what you would do otherwise. Is the tip is like, if it looks in your data that they are well separated, then probably your model is going to work well. Here you see that the wave that we gather, so the wave is this like, is actually not very trivial motion to see in the data. Yeah, so like wave, it should look like this. But it can also look in very different ways and can easily be confused with a snake. So wave and snake is basically just different planes in the space. So that's what it also ends up often confusing. Then in the deployment, as I said, this is as easy as it is. You pick your deployment platform, and here you have a bunch of things. You can also just deploy it locally. You can port it to C++ with no external dependencies, and then try to test it on your machine to see that everything is as it's supposed to be. And as I said, for the kind of hobby level things, there is a great support for Arduino, and one of these like sense boards is perfect for that. And Arduino you can run on a simulator also locally. Then you pick a compiler, and here you pick this quantized, and it creates a job to build it, and then you can launch it. So I think it's really good, and for me it's been enough with the free plan. It just limits you in projects and some of the classifiers. One thing is that you can also, like in here, and you create your, now it's done the training, right? When you create your model, here is the sort of vanilla way of doing this, making the neural network classifier using input layer, dense layer, and then output layer. So really simple. You can both kind of play around here with their click, so no code, but you can also bring your own model here. So it can be anything from Python that you can test. So if you have some kind of algorithm that you think could be cool to try to run on edge device, this is a very quick way to get started. Yeah, I think I'll stop now for questions.